Bem, muito boa tarde, boa noite a todos e todas. É importante estar aqui presente hoje, porque mais uma vez nós tivemos uma celebração na última sexta-feira, comemorando um dos importantes professores desse instituto, e hoje nós poderemos comemorar novamente, no melhor sentido da palavra, que é nos lembrarmos juntamente da obra do professor Darcy Swizzer, que dedicou a sua vida aqui dentro desse instituto a estudar kimberlitos e diamantes. Foi um dos primeiros petrólogos brasileiros ou mineralogistas brasileiros a trabalhar com inclusões de diamantes já nos anos 70. Essa, como parte nós teremos uma exposição logo depois ali no bloco F, na entrada do bloco F, com alguns posters, material que vai ser disponibilizado para todos poderem atender, mas hoje, um outro motivo de comemoração é que nós temos aqui um dos grandes expoentes do estudo de rochas do manto que nós temos no planeta, que é o professor Graham Pearson, da University of Alberta, e que hoje estará aqui nos oferecendo uma palestra que abrirá as atividades desta exposição. Mais do que isso, o professor Graham trouxe do Canadá algumas amostras para ceder à exposição. Então, nós teremos a última amostra para completar a nossa coleção, cedida pelo professor Graham Pearson, que logo passará essas amostras aí para vocês. Então, eu queria dar as boas-vindas. It's a great pleasure to have you here again. And Professor Graham Pearson stayed here at 2019, and he offered another talk to us, and today he will offer the talk of diamonds and the origin of cratons. So Graham, please, it's a pleasure.
Thank you, Rogerio. It is a pleasure to be back visiting your department again and the lovely campus you have here. So I'd like to start by saying that it's an honor to give a presentation to celebrate the opening of an exposition that's dedicated to Professor Darcy Civicero. Yes, those of us that work on diamonds know that his PhD thesis published in and completed in this department was the very first study of diamonds and their inclusions in Brazil, especially the inclusions. The first compositions of the inclusions were measured here by Professor Civicero, and that really kick-started diamond research in Brazil, of which he was very much a leader. And so as part of my own small presentation to the exposition, I brought along a nice sample of Canadian kimberlite from the Diavik diamond mine. It does not have a diamond, but it has a very large chrome dioxide crystal that I gave to you. You can pass it round and we'll see it. Sample. Thank you.
Everyone to see. Thank you very much, Graham.
Yeah. And if my talk is not interesting, you can look at the rock. Okay. So what I would like to talk about, last time I came, I talked about kimberlite, so I won't say very much about kimberlites in this talk. I'd like to talk instead about cratons, and in particular, what diamonds can tell us about cratons. So these very small crystals, as I hope to convince you, can tell us a great deal about much larger masses called cratons. We all know that diamonds are intimately related to cratons. And so on this map, the cratonic regions are shaded mostly in brown and gray, and the more extended cratonic regions with the red lines. And you can see that there is an excellent relationship between diamond mines, indicated by these diamonds, and circles are where the alluvial diamond mines are, and the presence of cratons, these ancient pieces of Earth's crust. But the origins of the cratons themselves, and in particular the roots that underpin them, are still quite controversial, and that's the topic that I want to discuss, in particular what the diamonds that are mined in these places can tell us about the deep roots beneath the old cratons. So we know most diamond deposits occur in kimberlites. I had to show one picture of a kimberlite. So this is a very nice fresh kimberlite, that sample that is passing round. would look something like this, with lots of olivine megacrysts set in a fine-grained matrix. These olivines may come from pieces of the mantle xenoliths like this that disaggregate and break up to become part of the kimberlite. There's a nice chrome diopside. This is from the same kimberlite as the piece of kimberlite that I'm giving you to look at. So today we'll focus on the cratons, and a good example, a simple example of a cratonic region is in southern Africa. So this is the lower end of Africa, in the South Africa, Namibia, Botswana region. And I've outlined in red here the greater area that we might call a craton. Now that includes, in fact, the people in Brazil are much more advanced in their thinking about cratons than in most areas of the world, because your cratons are slightly more complicated than in many areas. It used to be in southern Africa, it used to be thought that this was the only bit of the craton here where Archean rocks are preserved. But it's now much clearer, and I hope to convince you why. We define the craton and the cratonic lithosphere as a much broader area that encompasses both Archean, the Archean nuclei to the cratons here, and the surrounding Proterozoic areas, including rocks even as young as Mesoproterozoic in age. This is the old crust then, and it is underpinned by these thick roots that are very stiff and rigid that do not take part in mantle convection. This is the mantle lithosphere underlying the old crust. The age of this lithosphere can be very similar in age to the age of the old crust there, and so they've been coupled together for billions of years. But the question is, how do they form? We know that they're old. What diamonds, some diamonds actually, a specific class of diamonds, can tell us about how craton roots are made. So those deep roots, those lithospheric roots, are made out of melt-depleted peridotite. So that's part of the Earth's mantle that has had basaltic melt extracted from it. And when you do that, you make melt-depleted peridotite in these roots. So here's old crust again. This happens to be a cross-section across the top half of Canada here. We've left the unimportant country down here out of it. We're not interested in those people. This is the important country here. And the cross-section is across here. So we have thick lithosphere underneath the Archean nucleus. And then as we move towards younger crust, we have thinner lithosphere. And all this is melt-depleted peridotite. In some areas, it has diamonds in its root. Okay, that's what that rock looks like. So all this is composed of a garnet hartsbergite. This is garnet, orthopyroxene, and olivine that forms this melt-depleted root. And in fact, the stability, the whole stability of this cratonic mass, both the crust and the root, is dictated by the properties of this rock. And so craton stability is largely defined by the lithospheric mantle roots, because highly depleted lithospheric peridotites are buoyant, more buoyant than the convecting mantle, so they tend to float above the convecting mantle because you've taken dense melt out of them. They're more viscous, and so they're very strong. They last for billions of years, and they preserve their identity for billions of years. So why not use this mantle root in the definition of a craton? And so that's now, at least what we do, is that we use the lithospheric thickness and the temporal stability of the lithospheric roots as an intrinsic part of the craton definition. So by my definition, cratons are coherent blocks of Precambrian lithosphere, typically stable for time periods in excess of 1 billion years, owing to protection by deep, at least 150 kilometers thick, lithospheric keels. And so that's the definition I'll use. And that definition fits quite well with, well, it fits very well with the observation that if you use seismology to look at the thickness of the lithosphere beneath the oldest parts of the cratons. You can see here, so this is an S-wave tomogram, a slice at 150 kilometers. I blanked out the oceans here. And the blue-purple colors are cold, deep peridotite mantle roots. And you'll see that these cold roots coincide if we map the global geology onto that seismological map. You see that the cold roots map extremely well, are extremely coincident with the occurrence of these, not just the Archean rocks, but the Paleoproterozoic and Mesoproterozoic rocks. This is a work in preparation with my colleague James Scott, where we define around 65 to 70 Archean nuclei that form parts of these larger composite cratons and supercratonic masses. Okay, why do we like the idea of a 1 billion year cutoff for the age of cratons? Well, that 1 billion year cutoff is consistent both with continent evolution and with the thermal history of the Earth. And in fact, those things are quite closely related. And so if we look at the evolution of the continental crust itself, this is the volume of continental crust produced through time. So this is back at, say, 3.8, 3.9 billion years when continental crust first started being produced. And it wasn't produced in a uniform way. It was produced in kind of a surge, starting maybe in the later mid-Archean and increasing dramatically in the Neo-Archean here. These two lines are estimates of crustal evolution growth or crustal growth, and that evolution, that growth is tracked very well with the accumulation of the lithospheric peridotite mantle keels underneath. It's not exactly coincident. There's a small offset here. We can get into that later. But what's important is that by 1 billion years ago, this is today, by 1 billion years ago, then the continents are pretty much finished growing, and the cratonic roots beneath those continents had also pretty much finished growing. And so the last billion years, I study Archean rocks in the mantle, the last billion years has been extremely boring if you're a piece of continental crust. That fits nicely with the thermal evolution of the Earth. So what I've calculated here is this is heat production in picowatts per kilogram. That doesn't sound like very much, but if you scale the Earth up to weigh on the order of 10 to the 23 kilograms, that's actually a lot of heat that's being produced. That heat is being produced by potassium, thorium, and uranium decay that produces most of the Earth's radiogenic heat. And if you calculate the decay of that heat production through time, so here is the birth of the Earth at 4.5 billion years. And so heat production declines steadily. This is a log scale. If you look at that on a linear scale in terms of the factor of change, so 4 billion years ago, there was 2.5, well, over 3 times the heat production that there is today. And actually then if we look at 1 billion years ago, then here we have after 1 billion years, heat production has declined only 25%. And that's because most of the radioactive isotopes that produced most of this heat have decayed. The uranium-235 and a lot of the potassium has decayed away. And so much of the heat generation capacity of the Earth disappeared in the first 2 billion years of Earth history. And again, after 1 billion years, there's less heat. There's less heat to drive geodynamics, and in particular to drive the mantle. So how does that affect lithospheric evolution of these continental keels? Well, because actually, if we go back to 3 billion years ago, when many of these continents first started to appear, there was a lot more heat generated. And that heat did something, it heated, the rocks are hotter, the lithospheric keels are therefore weaker, because if you heat rocks up, they become weaker. And therefore, it's less easy to make cold, stable continents unless you have special conditions, which I will show. So here, for instance, Claude Jopar's group in France have done a lot of the fundamental modeling of this. Earth's early high heat production leads to transient geotherms. So what I've drawn on here, well, Jopar has drawn on here and I've reproduced, are a series of geotherms, plots of the temperature change with depth going into the Earth's lithosphere. And so you can see 3 billion years ago, we had higher temperatures at any given depth than today by some considerable amount because all this radiogenic heat was being produced. But it's a complicated issue, and in fact the equations that deal with this are very complicated. But to summarize them, there are two sources of heat that are interplay with each other here. There's the heat coming from beneath the lithosphere that's pushing heat upwards, but actually that is being more than counterbalanced by heat coming from above. All the potassium and uranium in the Earth, 99.5% of it, is focused in the continental crust. And so that is producing heat, and that heat is diffusing downwards. And so that upward and downward diffusion of heat is what's making these very complicated shaped geotherms. They're not linear, and we would call them transient. And what I'll hope to convince you of is that they remain very transient for very, very long periods of time. They are not steady state geotherms that we typically simplistically draw in the cratons. And so you could summarize that by saying that Archean crust had much higher heat production than today. Much of that heat actually never reached the base of the lithosphere because as the heat is diffusing downwards, the radioactive elements that are producing up here are decaying away too. And so there's again this interplay between diffusing heat downwards and decreasing your heat source. And so the base of the mantle, they never reaches the base of the mantle root because thermal diffusion, the time scale of thermal diffusion is similar to the half-life of the heat-producing elements. So below the crust, temperatures in the mantle root, this thick root underneath, will never reach the levels predicted by steady-state calculations. And as I've said, therefore the geotherms that underneath thick protonic roots are transients for most of their lifespan, actually. So you may see papers like this, where they come up with interesting conclusions that the different colored lines are different times, and they say that, well, there was a difference between the thickness of Earth's lithosphere in the Archean versus today. But the problem is these guys impose an instant steady-state geotherm 3 billion years ago. And so these models are wrong. Instead, you have to use a much more sophisticated approach pioneered by Claude Jopar's group, where you realize that this is a complicated plot of time, and this is the ratio of the temperature that should be reached at the base of the lithosphere to the temperature that is actually released. So it's the actual temperature divided by the maximum possible temperature. So if all that heat from the crust reached the bottom of the mantle root, then the value should be 1. You're producing heat that is reaching the base of the mantle root. But that never happens because those radiogenic heat producing elements are decaying away. And so depending on the thickness of your lithosphere, here for 150 kilometers or 220 kilometers, you only reach some maximum temperature that is not the theoretical maximum after 1 billion years, and for 220 kilometer thick roots, over 2 billion years it takes for you to reach peak temperature, which is only 70% of the temperature you should have reached by steady state. Okay, that's all very theoretical. Why does it matter? Why do we care about that? Well, it turns out that that really dictates whether you get diamonds or you get graphite. So whether you get these beautiful diamonds here from Saskatchewan, this is a Saskatchewan kimberlite from Canada, with all these amazing diamonds, they are stable in a cold, stable, rigid lithosphere. But if that lithosphere remains warm, then you get this. This is a graphitized diamond, in fact. So all the carbon in that diamond has turned to graphite, and it's now a paramorph of what used to be a diamond, but is now graphite. And of course, this makes a difference between whether you have a $10 billion diamond mine, $50 billion in some cases, or whether you don't have any mine. So the theory matters. So a lot of these geotherms that look very nice and linear that we calculate and fit through modern day mantle xenolith suites, they're okay for the last 500 million years of Earth history, but they're not applicable to the early history of the Earth. And the reason that matters is because it affects how we think about how the cratons are formed. So it turns out defining what a craton is a lot simpler than working out how they form, because they've had 3 billion years of evolution and the rocks continually get reprocessed. They have a very complicated message. But the two end-member models that are prevalent are that the thick roots beneath the continents may have formed by plume melting. So you have a hot mantle plume that melts to provide residual peridotites that dock or accrete underneath the crust here to provide a thick lithosphere. Or alternatively, you have slabs coming in from the side, subducting under some nucleus, and that slab stacking could also produce a thick root. And so those are the two end-member models we'll try and take a look at. Some more theory, but don't worry, I'll show you some diamonds shortly again. But the theory behind this or this can be summed up relatively neatly by one-dimensional thermal models. So these are thermal models where this is temperature, this is depth. We have an initial fairly thin lithosphere here, which is this straightish line, and we put a hot mantle plume under there with a potential temperature of, say, 1750 degrees. This is the Archean. And then we let that cool down. So we park a hot piece of mantle there and we let it cool down. In this situation, we have an initial lithosphere present and we stack two slabs underneath. And you can see life is much more complicated. But the two key differences are, in this situation with the plumes, things are cooling down. And in fact, they take a very long time to cool down. So this is 3 billion years ago. You only just start producing lithosphere that can get into the diamond stability field at 2.5 billion years ago. And even at 1 billion years ago, you've got a relatively small diamond window in here, the difference between where diamond is stable and the bottom of your lithosphere. In this situation, these very complicated lines are because you start out with an initial zigzag pattern and you heat things up. So you've put a cold slab under here and you're heating things up. We're also running down the radioactive heat production in these models as well, which makes them more complicated, but that is in the model. But essentially, you cool down in plumes and you heat up over a long time period for slab stacking. These conditions, in essence, produce much cooler conditions than these early in the history of cratons. So you could express that in a different way. What is the temperature difference at 150 kilometers relative to this diamond stability line? So the diamond stability line is temperature sensitive. So what is the temperature difference between your mantle of 150 degrees? Here, is it hotter or cooler than where the diamond in line is? And you can see that in this situation, you start out in the plumes with high temperatures and you cool it down. So after 500-600 million years, only just then do you get diamonds. In the slab stacking model, you start in very cool conditions, and for 2-3 billion years, you're always in the diamond stability field. So that should tell you something about what you might predict in terms of the presence or absence of diamonds. Okay, I said I'd show you some more diamonds. Here they are. So we can test these models. Those are theoretical models, but they're useless without real geological samples to test. You can do all the math in line, but as we're geologists, we want some samples in our hand that we can test our hypothesis with. And in this case, we're going to look at diamonds, slightly different diamonds though, because so in Brazil, most of the diamonds that you have, they may have formed 1, 2, 3 billion years ago, but they sat in the mantle and they were only brought to the Earth's surface in the Cretaceous of around about 90 million years ago, maybe 120 million years in some instances. So they have this very long residence time in the mantle, and so they see everything that's happened to the mantle lithosphere in that time. That's nice in some ways, but it's not good for telling you about the thermal properties right at the start of continent formation between 2.5 and 3 billion years ago. For that, we want diamonds that were made in Earth's mantle and extracted from Earth's mantle in Archean times, very early on in the history of the continent, because they give you a snapshot of what is happening in the earliest continental roots. They're the recorded early lithospheric thermal conditions. So as it turns out, there are a number of locations and examples that have such diamonds. The problem is they're extremely small. If you've been looking at the photographs, you'll see this is 0.1 millimeters. And so this diamond is maybe 0.2 millimeters. Very, very small diamonds here from different locations. This is a bigger diamond. It is maybe 300 microns with some garnet and some olivine inclusions. So this is why you need students, because when you become old like me, you don't see so well. And so you need young students with better eyes than I have to work on this stuff. So just as an analogy then, so this is a more normal diamond where if students are lucky, they've got big diamonds to work on and their inclusions are maybe 200 microns in size. Unfortunately for my students, their diamonds are the same size as the inclusion in that. And then we are looking for inclusions in these diamonds that are much, much less than 10 microns, maybe 1 micron in size. And so life is very difficult. On the flip side, it doesn't matter so much if you lose one of those diamonds. It's less than 1 cent. You lose this diamond, it's a problem. Okay, so Canada is a good place to do this work because it turns out we have 3 locations throughout Canada where we find such diamonds: in the Northwest Territories here, up on the Arctic coast, in Manitoba, and in Ontario. All these are diamond locations where the diamonds were made in the Archean, and they were brought to the Earth's surface also in the Archean. So they retain that snapshot picture of the thermal conditions in Archean times. So here's one location, the Tree River location. This is the Slave Craton here, so up in northern Canada. Very complicated Archean geology. So we sampled an Archean conglomerate here. This conglomerate has gold and diamonds, just like some of your Brazilian conglomerates, but these are much older. And these basal conglomerates have diamonds. The first sample we took of 15 kilos, we got 3 diamonds from the sample. These are cathodoluminescence images of the diamonds polished through the middle. These are the diamonds. And then in subsequent samples, we found 30 or more diamonds, also in very small sample sizes. So although the diamonds are small, they're quite abundant in these samples. We know that the diamonds were extracted from Earth's mantle because, well, if you're a stratigrapher, you can use simple stratigraphy and say, well, they occur in sediments that are just above this very old 3.3 billion year basement here. If you want to be more precise, you can do detrital zircon work on the zircons in the sediment. So these are a bunch of detrital zircons. And the important information here is that there's a big peak in the zircon age population at 2.9 billion years. And the youngest zircon, which gives the sort of maximum age for these sediments, is something like 2.83 billion years. So those diamonds were in a sediment at 2.83 billion years. So any thermal information they contain is telling you about the thermal conditions in the mantle at 2.83 billion years. How do we get the pressure and temperature information? So that comes from my colleagues at the University of Padova in Italy, and they have been working a lot with a technique called elastic geobarometry. And it relies on the fact that at room pressure, a diamond with an inclusion, so the diamond is here, this is an olivine inclusion, and because of the difference between the way the diamond expands relative to the olivine when the diamond is brought to the surface, This olivine is under pressure, which is very useful. So the elastic geobarometry, we have an inclusion in a diamond at the pressure and temperature of crystallization. We have decompression and cooling as the diamond is brought to the Earth's surface. We then have a diamond at the Earth's surface with an inclusion that tends to expand more than the diamond, or tries to. The diamond is keeping it trapped, and so there is a strain relationship set up, and the inclusion becomes subject to, it is under pressure. 1 gigapascal pressure, very high pressure in some of these diamonds. That's why some diamonds will explode when you try and polish them to expose these inclusions. They just go bang. Okay, and so these are the details of how we extract the pressures and temperatures. I won't bore you with the details, but that's how it's done. And the important reference here is by Ross Angel, 2017. We measure the pressure, in effect, by measuring the atomic spacing in the lattice of the olivine. So how much the atoms in the olivine are compressed because of the pressure exerting. So there's a tiny olivine in that inclusion, about 3-4 microns in size. It is impossible to see with eyes, even students' eyes. So you put it in the X-ray machine and it reveals there's an olivine there, but it also reveals by X-ray diffraction and the atomic spacing that the pressure on that olivine in that diamond is between 1 and 1.5 gigapascals. That gives us a depth which is somewhere around here. Then, using nitrogen impurities in the diamond, and again, I don't have time to explain exactly how this works, but with time, every diamond traps nitrogen impurities, and with time and with heat, these nitrogen impurities want to meet up to make pairs and quadruple aggregates of nitrogen. That's a temperature-dependent process. And so from the way that the nitrogen atoms are aggregated, we can calculate that the temperature, the integrated residence temperature of this diamond was somewhere between 1159 and 1168. Now that sounds really quite precise, and that's because it is quite precise, because these are very young diamonds. We can constrain the maximum time that they've spent in Earth's mantle, and this gives us a very precise temperature and pressure that is every bit as good as you can do with taking an electron probe and calculating using thermodynamics, the pressure and the temperature. So we have well-constrained lithospheric conditions for diamond formation and residence, and they imply that the geotherm, or at least not the geotherm, but the pressure temperature point was in very cold PT space. These are modern day geotherms here for different crustal heat flows. They're not relevant to 2.8 billion years ago, but they tell you as a reference point that those PT conditions are as cool as the PT conditions in modern lithospheric mantle. So the next location is in Knee Lake in Manitoba. So here is the Superior Craton. Manitoba is here, and there is a very strange alkaline rock there that has thousands of diamonds, but unfortunately they are 100 microns or less in size. So those diamonds look like this. They're very strange diamonds. They're odd growth shapes. There's a lot of cubo-octahedra and cubes. There are some octahedra with some dissolution pits on them. And very rarely, if you look very hard, you can find garnet and olivine inclusions in those diamonds. This is work done by my student, Andrea Pizzara, that's just been published in the Kimberlite Conference proceedings. So these diamonds also were extracted at about 2.7 billion years from Earth's mantle. This is a plot of how many diamonds versus diamond size. It's a very disappointing plot if you're searching for diamonds. When people first tested these rocks, they found thousands and thousands of small diamonds. And sometimes, even though you've got many small diamonds, in this case, this is number of diamonds per 100 kilograms, if you extrapolate the curve, hopefully, somewhere down here, you get diamond masses that are quite big, even though you don't have very many. That's how you predict. That is one way of predicting how economic your diamond mine is. Unfortunately, for the black curve on here, Knee Lake, the diamonds just stopped. There are no big diamonds. There are thousands and thousands of very small diamonds, but there are no big diamonds. So useless for economic considerations, but very useful scientifically, because it means that the company that found these diamonds just gave us the diamonds. They're worth nothing, and we can study them. And again, we can calculate pressures and temperature conditions from the inclusions in those diamonds. In this case, more conventionally, actually, these are pressures and temperatures calculated from olivines and garnets. If you measure the elemental composition and the way that changes with pressure and temperature, you can come up with a precise estimate. But again, this is the graphite diamond curve. These are modern geotherms, and it gives you very cool pressure temperature conditions. And so Andrea, my student, came up with a model where to get those cold temperature conditions at high pressure, then you have fluids being taken down by a subducting slab, and those fluids interact with the lithosphere to make the diamonds. That's a model. We'll test those models. We'll look at how valid those models might be with real thermal models. And then the last occurrence is in Ontario, in Wawa. These are much nicer looking diamonds. And if these were 1,000 times bigger, this would be a diamond mine. But they're not. They're all this size. But again, they contain inclusions. They contain inclusions of lithospheric minerals, garnets and olivines. The olivines here, these are the Wawa olivines. They have just the same compositions. This is magnesium number, magnesium over magnesium plus iron, just the same compositions as global lithospheric diamonds. Interestingly, though, the garnets here, these are the Wawa garnets, these circles, they have a little bit too much silicon for a garnet. And when you calibrate aluminium and chromium plus silicon, you have a barometer called the Majorite barometer, and that puts the pressure needed to form these garnets at 250 kilometers or even higher. So very high pressures at actually quite cool temperatures. So if we look at all these three occurrences and we take the pressure and temperature estimates from all three occurrences and we put them on a modern day, on a pressure temperature plot, this is a modern day geotherm. It is not relevant 2.8 billion years ago. It is a reference for cold lithosphere today. We see the Tree River and Knee Lake PT conditions are exactly equivalent to the coldest of modern geotherms. And if we plot Wawa on there, then the deepest of the Wawa samples is way below it, very cold PT conditions. Okay, so with that information from the diamonds, then we can take that information and compare it to our thermal models. So here are our thermal models again. This is the hot plume with the cooling down of plume residues. And even after 3 billion years of cooling to something like a steady state geotherm, you never get to these cold PT conditions. It's not possible. The only way you can produce these PT conditions, note the slight difference in scale here, is by stacking cold slabs. You put one cold thing against each other, you have a much bigger cold environment that will slowly heat up. And so the only way of producing these PT conditions at 2.8 billion years ago in the ancient Earth is by stacking cold slabs together and having those slabs warm up over billions of years to something more like present-day geotherms. Although even then, these are after 2 billion years and after 3 billion years here of evolution, even these geotherms, after 3 billion years of thermal evolution, they're not truly steady-state geotherms. They're transients. So cool mantle root conditions that are required by Archean diamonds are most readily achieved by the stacking of 2 or more slabs in complex transient geotherms. So you can have any model you like. This is with 3 slabs, this is with 2 slabs, but the slab stacking model will always produce these cold PT conditions. The plume cooling will not. This is a more complicated way of saying exactly the same thing, which I won't do. Okay, but if you know anything about mantle melting, you're going to say, well, maybe there's a problem with my argument, okay? Because what I've done, I've just calculated a fairly simple, the mathematics are not too simple when you put the radioactive decay equations in here, but a fairly simple cooling model. But there's an extra cooling in mantle plumes. That's because when you melt Earth's mantle, you actually cool the residual mantle down by an effect called latent heat of cooling. This is how that works. So this is depth, this is pressure. If you take a portion of mantle, and most mantle melting occurs because you upwell the mantle, you intersect the solidus, the melting point, and when you do that, and melting occurs, you take heat out of the system, latent heat of fusion. And as a consequence, that piece of mantle cools down. So we modeled that very carefully using the MELTS program, working with Paul Asimov. The MELTS program allows you to calculate that cooling effect. And while it's fairly considerable, it's nowhere near enough. And in fact, most of the cooling occurs at shallow depths because most of the melting occurs at shallow depths. So at depth, you get a little bit of a cooling effect, maybe 50 to 100 degrees. And in the shallower mantle that you might produce by high pressure melting, you might get cooling to 150, even 200 degrees. But it's still nowhere near enough to then cool that system down to get you into this condition of cold PT conditions. So any way we can think of trying to modify this mantle plume hypothesis doesn't work from a thermal perspective. So I'm not saying that you cannot produce any lithosphere by mantle plumes. You must produce some. What I'm saying is that you can't produce the lithosphere that hosts these diamonds because it can never be cool enough to host the diamonds. What's the other evidence for what I'm saying? That the diamonds are forming in cold lithosphere, and that cold lithosphere has originated by stacking slabs. When you stack slabs, you take things from the crust, you push them to greater depth, and you put crust into the mantle, and in that way you can make diamonds. And we can track that process using a combination of carbon isotopes here. This is delta 13C. It's a thumbprint of where the carbon has come from. And nitrogen isotopes, which is also a thumbprint of where the nitrogen has come from. The green box is where diamonds that are made solely within the mantle should plot. And then here are the data for Wawa. There's one location in Witwatersrand with also a little bit of data, and the Tree River data. And you can see that all the data we have so far for these ancient diamonds plot outside of the mantle box. They have very crustal-like nitrogen isotopes, and some of them have very light carbon isotopes, which can be explained by interaction between these two crustal members and a little bit of mantle carbon that is making diamonds from the crust, from the crustal carbon that you're subducting when you stack these cold plates together. So this story is consistent with the thermal story from the diamonds. Okay, so conclusion from diamonds erupted in Archean times is that slab stacking is the only realistic way of producing the transient and very cold conditions recorded by these diamonds in the deeper lithosphere. Plume melting residues might have contributed to making these roots, but those roots could not have hosted diamonds until well after Paleoproterozoic times, often in many cases well after Mesoproterozoic times. And so if there's one thing to take away, is that transient thermal conditions prevail beneath cratonic roots for much of their lifespan. There's never a steady state in cratons. You will see lots of papers where they plot, I've even plotted them myself, these nice linear steady state geotherms. I don't think they can ever exist, actually, when you calculate the thermal inertia of these large masses. These include the inclusions extracted from very small diamonds that come out of cratonic lithosphere in Meso to Neo-Archean times record cool, transient lithospheric thermal conditions. That and their carbon isotopes suggest a subduction origin. And the thermal modeling of these various scenarios are most easily matched by slab stacking, very difficult to achieve by plume melting. So in summary, Professor Savissaro is correct. Diamonds tell you a lot about cratons. Thank you.
Thanks a lot, Graham. Can we open for some questions? Sure. So, se alguém tiver alguma pergunta para fazer, por favor. Lucas?
Hello. Thank you for the presentation. It was nice to hear you. And I have some questions about how photospheric stacking can be more effective to do cratonic queues, because it seems that you are adding some oceanic material together with the lithospheric queue.
Yep.
And it can increase density, it can result in lithospheric delamination.
Yep.
And it seems more difficult to think this process to produce a thicker cube.
Yeah, no, that's a good point. I mean, if you're naturally creating what you would think would be a less dynamically stable situation here. But in fact, I couldn't email the files to myself because they were too big, but you have a much more severe problem here actually in terms of dynamics, because what comes with this is the fact that there's so much energy in those plumes and so much buoyancy that I have a model, geodynamic model that shows this. As those hot residual peridotite come up, they will not stick underneath the crust. They just disappear into the mantle wind because they're very weak, they're very buoyant, and the dynamicism in that system is so much that they just dissipate. So however this works, and you're right, these are the earlier stages. I think what happens here is that you don't just do that. It's slightly more complicated. So you don't just put one slab underneath another and hope for the best. You do that and you compress the thing at the same time and you kind of weld it together. And that process appears, if you look at the history of any craton, you can see this fabric in the superior craton is a good example, where the geological grain or fabric is extremely consistent right across the superior craton. And that's because these individual blocks have been brought together laterally, and they've been accreted and almost welded together. And so you appear to produce these thick roots. And that process, the final accretion process, when you squeeze this, appears to do a good job of stabilizing that root, much more so than you can do in this situation, for instance.
But it should produce a lithospheric cube that is not so strong as it should be if it was isotropic, right?
So the strength is largely controlled by the depletion in the olivine. Yeah. So I think that when you accrete and squash the craton, you drive the volatiles off. So you have some initial melting that comes with that. And when you convert from, say, wet olivine to dry olivine, then you have a very strong cratonic mass there, which is so it's the strength comes from the compositional factor from the olivine. Forsterite 93 olivine with no water is 2 orders of magnitude stronger than Forsterite 89 olivine with a 200 ppm water.
And it's more buoyant.
It is much, much more buoyant. Both these systems will produce buoyant peridotite.
Yeah.
But and they could produce fairly similar looking residues. But we've tried hard to make roots using plumes, and you can do it, but you need a trap. You need the buoyant residue to come up, and you need a thin spot for it to stick into. So you need pre-existing stuff to trap it. So you get into this chicken and egg situation.
It can be a cumulative effect as well, because
it can, yeah. But for each pulse of this plume, it's very hard to get one of these residues to come up and stay exactly underneath. Yeah, even if you play around with the rheologies, they disperse into this flat pancake. So some portion of the lithosphere could be that residue, but it is impossible to build the thickness that you need. And even with simple thermal models, there's no way you can get anywhere close to those thermal conditions.
We have one more question here.
Hi, it was a very nice presentation. I'm just curious about these labs. How would they occur naturally? Like, go on top of each other?
Yeah.
A natural rain or something?
So the Archean Earth could be a potentially fairly dynamic place where there's a lot of melting going on. A lot of melting that's going on might be at these proto-ocean ridges. So you have some sort of spreading center that's producing proto-oceanic crust, if you like. So it's not modern-day plate tectonics, because modern-day plate tectonics has very cold lithosphere that can descend into the lower mantle. That's not what's happening here. This is lithosphere that's been produced that's warm enough that it's actually quite hard to subduct. And that's why you stack the slabs, because it's still warm enough that you don't produce the sort of densities for the slab to just do that and descend into the lower mantle. So that's being produced in the Archean. Even the ridges, if there were ridges there, they were hotter than the modern day, and they're producing plenty of melt, and that melt produces plenty of residue. So you have melt residues being produced in abundance. So whether you want to call it oceanic lithosphere or not, if you have any decompression melting beneath a fracture, you're going to make lithosphere, because that melt residue accretes and makes lithosphere, and then any collisional forces will bring those plates, those proto plates together, and you'll stack them.
So thank you very much, Graham.
Okay.
Julia.
There's a question from the YouTube now. This one is from Lorenzo Douglas. He asks, what may have happened to the Earth that made meteorite rocks stop appearing after the new Proterozoic?
I'm not sure they do stop appearing after. I'm not sure I fully understand the question, because mantle-derived rocks appear right throughout Earth history. Does the person asking the question want to qualify the question a little more? No? Okay. Yeah. But rocks from the mantle are made from the Archean times right through to today. Yeah. So I'm not sure I understand the question.
You got it. Vamos. Bom,
Should find a sample.
yeah. Where is the sample? So, pessoal, eu só gostaria de agradecer o Graham. Eu tenho apenas alguns minutos aqui para falar e agradecer a vocês. Convidar vocês para verem depois essa exposição, que é Kimberlitos e a Origem dos Diamantes. E como vocês podem ver aqui, essa é uma exposição de amostras da coleção, principalmente a coleção internacional de Kimberlitos do professor Darcy Visser. Então são exemplares de amostras que, depois que ele faleceu, né, estavam na sala dele, bem catalogadas, estavam todas elas bem cuidadas. Estava lá eu e o professor Fábio, que estávamos lá, fizemos um levantamento disso, e é importante demonstrar isso para todos. É interessante que temos uma parceria nessa exposição com o pessoal do museu, o Miriam e Deval, todos os voluntários e todos os estudantes que trabalham dentro do museu, eles também nos ajudaram a catalogar essas amostras e organizá-las e mostrá-las. Quando nós submetemos esse projeto para a Pró-Reitoria de Cultura e Extensão aqui da universidade, nós pedimos alguns recursos para termos essa exposição associada ao museu como um módulo educativo. De toda forma, o que nós conseguimos fazer aqui e trazer um material informativo, aberto a todos os públicos, e que, principalmente para os públicos que são não geológicos, e que podem aí entender um pouco mais, ou pelo menos visualizar um pouco, o que são, como se formam os kimberlitos, e como eles conseguem, de altas profundidades no manto, trazer essas rochas para a superfície. Então, apenas para realçar que kimberlitos, embora são rochas raras e bastante complexas, mas não obstante a sua complexidade, essas rochas atraem muito a atenção justamente pelo seu potencial econômico, por trazerem consigo uma série de diamantes, por isso que são tão estudadas, bem como uma série de xenólitos do manto de diferentes profundidades. E isso é muito importante porque os kimberlitos são os magmas que têm o potencial de ser os mais profundos que nós conhecemos. Por isso eles conseguem amostrar muito do manto que nós conhecemos e principalmente, né, a partir de inclusões em diamantes, conseguimos ver diferentes fases minerais que são estáveis nas profundidades, pelo menos até 440, 660 quilômetros de profundidade. Bom, nessa exposição, o que a gente tentou fazer, né? Mostrar esses kimberlitos, mostrar... existe no novo museu, vocês viram lá, tem uma estante só com diamantes já polidos, né? Mas há também alguns diamantes que são expostos nesses cubos que a gente colocou ali, não lapidados, e que estão ali à disposição para ver como que os xenólitos e os xenocristais, principalmente xenocristais, diamantes, são carregados pelos kimberlitos e trazidos até a superfície. Veja que nesses objetivos, né, a ideia justamente é esclarecer dúvidas do público mais leigo acerca de ocorrências kimberlíticas. E o que a gente espera é que isso possa despertar o interesse científico, né, do público universitário e mesmo daquelas pessoas que estão vindo aqui ao Instituto de Geociências, que possam pensar um pouco como que cristais que são tão raros e que são trazidos de profundidades tão grandes do nosso planeta podem chegar até a superfície. Essa exposição, ela traz amostras de mais de 10 países diferentes, da maioria dos continentes, e mesmo das amostras que nós temos do Brasil, a gente consegue estar apresentando elas em diferentes regiões do Brasil, quer em regiões, principalmente a partir daquelas que estão em regiões cratônicas, que o professor Pearson mencionou hoje, mas também aquelas que estão bem nos limites de crátons e que também são diamantíferas, né, a partir das definições antigas do que é um cráton. Então, a ideia é que a exposição ela possa ser útil para a informação, cultura e esclarecimento de toda a comunidade. Nessa sequência, o que a gente procurou fazer, né, é basicamente mostrar o que é um magma, qual é a origem das rochas ígneas, falar um pouco sobre os magmas kimberlíticos, onde eles são gerados, o que eles têm de especial, o que são os kimberlitos, e a partir daí mostrar como esses kimberlitos, que são magmas que ascendem muito rapidamente, como eles conseguem amostrar tanto o manto quanto a crosta terrestre. A partir daí, obviamente, que a gente tenta mostrar um pouco o que ele carrega do manto, que são xenólitos e xenocristais. Entre eles, o diamante. Os diamantes são xenocristais trazidos do manto. E o que tem de especial esses diamantes? Então, a gente consegue comentar um pouquinho sobre eles. Por fim, para aproximar mais essa exposição do público em geral, o que, com uma série de ideias de pós-graduandos, de uma série de reuniões que nós fizemos, optou-se por colocar ali um personagem, como se fosse um avatar do professor Darcy, que ele vai acompanhando a exposição e sempre trazendo algum balãozinho com alguma mensagem sobre o estudo dessas rochas. Ao final, a gente mostra quem foi o professor Darcy, que pôde, então, estar sempre aqui trazendo. Se você, talvez você não conheça, não tenha conhecido o professor Darcy, mas se você entrar no Museu de Geociências, que foi reaberto ontem, você vai ver que boa parte das amostras, que não necessariamente são kimberlitos, também foram doadas pelo professor Darcy. Então, ele era um cientista brasileiro, renomado, conhecido internacionalmente, e que pôde trazer uma série de amostras internacionais para o nosso museu, e agora também disponível aqui aquilo que ele mais estudou, que foram kimberlitos e os diamantes. Então, nós fizemos ali também um módulo de homenagem ao professor Darcy. Porém, mais do que a coleção do professor Darcy, nós temos que agradecer a uma série de amigos, colegas e pesquisadores que doaram amostras. Então, o professor Graham Pearson foi um deles, né, o professor Valdecir Janazzi, professor Excelso Ruberti, todos eles estão citados aqui e puderam trazer. Professor Fábio e Eliane prestaram amostras do Museu de Gemologia para que pudermos expor aqui nessa exposição, depois são amostras que serão devolvidas, assim como também Leonardo, que está aqui do Serviço Geológico, trouxe uma amostra do Kimberlito Brauna, que são kimberlitos pré-cambrianos que estão na região da Bahia. A gente agradece muito também a funcionários, docentes do Instituto, que nos ajudaram muito nessa exposição, aos alunos e alunas que participaram, quer de forma voluntária, ao longo desses anos que nós estamos tentando montar isso, e aos órgãos de agência e fomento, como o CNPq e a FAPESP. Essa é a nossa equipe de produção como um todo, né? Estamos aqui, né, a Miriam, o chefe do museu, Ideval, está aqui junto, sempre foram parceiros nessa empreitada. Professor Fábio Ramos, que desde o início, né, foi um dos idealizadores, junto comigo, dessa exposição. Mas a Amanda Magrini, que é do curso de licenciatura, que sempre nos ajudou com o know-how que ela tem de exposições, né? Então, uma ajuda que ela deu, mas, sobretudo, eu queria agradecer muito aqui aos estudantes que têm trabalhado comigo ao longo desses anos, porque se não fosse eles, essa exposição não teria saído nesse momento. Foi muito esforço deles, se a gente está conseguindo estar aqui hoje, expor esse material. Então, eu queria agradecer pessoalmente a todos que estavam aqui, Cipó, Vinícius, Cipó, Vinícius, cadê a Heloísa, que catalogou tudo isso, Fernanda, Breno, que ajudou agora nesse final, e mais do que isso, né, eu tenho que agradecer muito a duas pessoas desse grupo, que acho que todos falam, além da Júlia, que fez para nós o glossário, e que estará à disposição, certo? E que esteve sempre junto conosco também, a Júlia, para trazer esse material. Agora, duas pessoas aqui puderam ajudar muito a fazer os textos que estão nos posters e a diagramar as coisas e nos ajudar muito, que são Amanda e Lina. As duas, elas ajudaram muito a gente nesse processo. Então, eu queria agradecer muito elas. São parte da equipe produtora, né, da exposição, mas agradecemos a todos, então, do nosso grupo Insaturados para estar aqui hoje. A vida do pesquisador, às vezes, ela é muito solitária, né? Principalmente num instituto como esse, né? Que é muito grande, né? E traz uma série de pessoas. O professor Darcy, ele era uma pessoa, tinha muitos amigos, mas por vezes a gente via ele sozinho, caminhando para lá e para cá, tal. Então, resgatar a memória de uma pessoa que pôde contribuir tanto e que é reconhecida internacionalmente é também resgatar um pouco de nós, da vida que nós temos aqui dentro desse instituto. Então, a gente pôde fazer isso na última sexta-feira com o professor Ubris, e agora é importante a gente fazer isso. A gente demorou um pouco para conseguir fazer isso, né? Teve os anos da pandemia aí, depois a gente foi se acertando, mas felizmente nós estamos todos aqui e conseguimos fazer isso. Então, a finalização nós precisamos da amostra de voto para todos irmos lá colocar essa última amostra lá na exposição, e eu agradeço a todos por terem vindo aqui e peço que todos possam ir lá, dar uma visitada lá na exposição junto conosco. Tá bom?